Thank you very much. Let's try to go through today and we'll get to 100%. Thank you very much for the invitation. I'll join the chorus and say that thank you to the organizer, very inspiring meeting. And with my eclectic taste, I like all the different aspects of it. It was great. So what I want to talk to you about today is brain. For a few years now, but maybe 4 or 5 years, we've been looking at various aspects of the brain. A few years ago, in 2013 or so, we started a network of people interested in that from different disciplines, just trying to gather and have some meeting with clinicians, biologists, physicists, and so on. So if you're interested, we wrote 2 reviews on the subject. What I'll be focusing today is just modeling brain and skull. There's plenty to say about the brain. I hope I'll get to the skull, which is the latest part. It's work I've been doing with Ellen Kuhl, who couldn't be here this week, when I was visiting last year in Stanford. Most of it, but it's also the result of many interactions over the years with different people. So let's start right away. This is a brain. It's the brain of an 83-year-old who died of dementia. Just want you to see what it is, because usually we have a very clean and clean view of the brain. Or if you take a brain out of a skull, that's what it looks like. It's quite complicated, very nerved. The blood system is incredibly complex. Here you have enlarged cerebellum, as you can see, the frontal lobe. See, this is the structure. A natural question is, how do we understand this as a pattern? You can ask, is it important, is it relevant for science or medicine in general? But it's there, it's a structure that we want to understand. And for many people here, saying patterns and trying to understand it is by itself enough. So let's go into a little bit more detail. If you slice the brain, you'll see that you have 2 different zones. You have a mostly white zone, which is the white matter, and a mostly, it's not gray, it's going to be more red, but when you stain it or when you fix it, it's going to appear gray. And one of the well-known structures in the folding of the brain, here you see underneath, you see the cerebellum here, and what you see is just the white matter. So if you remove the cortex, this is just what you'll see, right? And if you add it, then you'll have the cortex and then the skull on top of it. And you have this structure where you have valley and mount. The valley are called sulci, or one sulcus. And the top, the mountains, are the gyri, one gyrus. And you see as it's fixed, it appears mostly white, for the white matter, and gray for the gray matter, which is rich in blood and cells. The white matter appears white because it's mostly fat, myelin, and things like that, or very closely related to. And so that's the same type that you'll find in normal fat. So this is actually, Ellen's is actually here. This is a brain. This is a 3D print of it. Come from segmentation, from MRI slice and segmentation. And this is the structure that we use for some of the simulation. So 2 problems that I want to study today related to growth and elasticity. The first one is an old problem that many people have looked at in the past, is brain morphogenesis. And the second one is probably a little newer that very few people have looked at, which is what is the relation between brain and skull, and how does the skull actually take its shape, and what is the mechanical influence on the growth of the skull. So the first observation that you see for brain morphogenesis is that at a certain time in gestation, typically around 30 months, between 6 months and 7 months here for humans, you'll see that gyrification appears. You start the onset of folding, right? And that's further developed over time, and even after birth, as we're going to see later on. If you look at the basic estimate, the basic numbers for it, you'll see that if you look at the evolution of the volume compared to the evolution of the surface area, the total cortical surface area, right around 29 weeks, you have a rapid increase of the surface area, which is really the onset of the folding. The area suddenly increased much faster. Of course, people have been looking at that for a long time. It's actually one of the very first systems that people interested in allometric scaling have looked at. Cyrus and Rameau, 1839, that was the first two-third law, respect volume and area type law. They were looking for the brain. This is really the prime example. And since then, people have looked at all possible measurement of the brain, the area, the volume, and so on, and done nice curve and scaling, and there's endless discussion about that. One of the most common one is the gyrification index, which is just the ratio between this blue curve and the red curve. So it's the length of the contour divided by the convex hull. And so it's bigger than 1, and that means you have folding. And if you look, for instance, in different species, of course, people would do comparative biology, love these kind of things. You can plot them in different scale against the body weight, for instance. You can put the log of the growth index. And of course, we're very proud because the Homo sapiens, we're right at the top, and you can then argue why we're superior in any ways. It's always the ultimate goal. If you look a little closer among the primates, you say you do have a trend like that. First, you see that among the small primates, so you're actually more or less on the same scaling law as they are. Actually, it's not that special to be human. Among the larger primates, it's different, and you can argue that gorilla and chimpanzee are actually very different for other reasons. But then you start adding other animals, and you see that maybe we're not that special, because the dolphin brain and actually most of the cetaceans are all up there, right? So this is us, and this is all up there. So gyrification, yes, we can understand we pack more cells, more neurons in that cortical space, and that can enhance cognitive function and so on. But dolphins actually have much higher gyrification than we do. Okay, so of course it's never the whole story. Nobody has been able to attach a single number to brain and claim something very deep or profound about it, right? But it's part of the picture. You can still try to understand the onset of this structure. So what are to go back a little bit in history, the competing hypotheses about folding, how does it occur? One of the first one, and what people thought for a while, promoted by people like Pappas and Le Gros-Clark. Le Gros-Clark was an influential anatomist from Oxford, and he published this kind of idea actually in a book that is presented, a series of essays presented to Darcy Thompson. That was the result of a meeting in Oxford around that time, dedicated to the life of Darcy Thompson. And his idea is that the folding is due to external constraint. Right? You have the brain expanding, and the skull resists to it, and since the brain cannot go further, it starts crumpling on itself. Right? But this idea was discarded already by Barron in 1950. So Barron, for years and years, did series of very nice experiments on sheep, where they would go and destroy part of the brain of the sheep during gestation and see what happened, including removing part of the skull, and noticing that there was no difference in the folding pattern. And that, for instance, sheep 409. Imagine the carnage there. Silence of the lamb or something. You know, yeah, it's the kind of things you wouldn't be able. I don't think it would be legally allowed to do this kind of experiment on ethical grounds these days. But I mean, these are great because these were exactly the question that we have. Biologists, of course, a very different question nowadays, but you want to see, well, is the skull important? Well, you remove the skull. Or is the cortex going to grow? Or you move part of the cortex or one side, and so on and so on. So a very nice series. But so that was discarded as a main hypothesis. Another one that is extremely popular and still very popular among people in neuroscience is that it's axonal tension that actually produced the folding, and that's due to this paper from 1997 from Van Essen. Van Essen is also very influential and today still very influential in neuroscience. He established atlas of different zones of the brain and so on. So this paper has over 1,000 citations. And the main idea is that very early on axons are established and they act like inextensible strings essentially, and as the brain expands, it brings different parts of the brain together. And the idea of Van Essen is that the proof of it, in a way, is that you see this kind of connection in the mature brain. The problem with that idea is that if you look and if you make dissection, if you cut like this, in very nice series of paper and experiment by Bailey, by the group of Bailey and Tabor, is that you don't see any residual stress in the brain or in the axon. If you do a cut like this, you don't see the material expanding, right? You have a little bit of residual stress in the other direction. So it seems, at least at birth, there is no indication that you do have this type of tension. If there is residual stress, it's actually very, very small. And in the same way, if you've looked at model or simplified model, or the radial spoke, it doesn't really improve much also. And you also have to take into account that we know we have ideas about the mechanics of axon and so on. So the picture, you cannot make a real model based on these ideas. But it's still very popular. So more or less the consensus in people who do biophysics and mechanics or for this type of problem is that it's really due to the cortical expansion, the rapid cortical expansion, and it's very much like the expansion or the growth of soft tissue bounded over another tissue of a different type. So the cortex expands faster than the substrate. And that was first proposed by Elliott Smith in 1928, but it was really expanded in that nice paper, which is the first real model of this type, that includes John Hutchinson that we know from engineering community in Harvard. This paper, however, assumed that the difference between the two, of the stiffness between the two, was very large in order to represent the pattern. So the story was incomplete. People mostly forgot about this paper, at least until 20 years later, people started playing again with this type of problem. So I want to go back here and try to understand, since we have a very mixed community here, I want to try to understand really the basic of that instability, or what can we understand. So let's go back to the simplest possible problem, which is the thin film problem. And the thin film problem is that you have an elastic substrate. You can actually think of it as a first as an elastic half space. And you bound to it a thin substrate. And then you can do different things on that substrate, on that. You can take the whole block and squeeze it. You can pre-stress the layer and then bond it. Or you can leave it like that and then grow it and so on. Whatever you do, if you manage to build compressive stress in the upper layer, you'll manage to build some type of pattern of this type. Wrinkle, crease, buckle is nice. There is a nice poster on creases, fold, and so on. So there is a lot of phenomenology. More or less, independently of what you do, you'll observe the same type of patterns at the same time, essentially, of strain. So these instability are really generic in the shape. However, the parameter value at which they occur, at which they first appear, really depend on how you do it. Right? And there is a lot of confusion in these communities because people do experiments by compressing block, and they say we observe such and such instability, hence the brain cannot be have that type of instability and so on. So you have to be really careful. The way you create this instability is actually really important in terms of parameter space and so on. So there are generic aspects, but the particular aspects are often different, and you cannot apply directly one idea to a different setup. It gets even worse when you consider the nonlinear response. This is just, in a way, the first linear response, but nonlinear response then depends on all the possible details of the problem, the nonlinearity of the material, the type of boundary condition, the way you apply stress, and so on, so forth and so on. So you have to be very careful there. So there's been very nice work. The relevant work for people like us is very nice work in early 2008, 2011 by Areski and his friends. Pasquale and Martin have done very nice work, and more recently Hutchinson and Ellen have also done just nice work, just trying to understand these instabilities. So it is a reference work. Yes?
Something about the normal forms of these bifurcations. Would you say that they were particularly complicated? Or
So it depends which bifurcation. The first one, it's more or less, as I'm going to show, a universal instability. But is it subcritical or supercritical? First point, right? That's already very complicated. And as you see, its instability disappears towards other instability. So up to a certain point, yes, you have a certain universality in there. And you can, for the first instability, you can collapse all of that in the right variable. So, you know, there is a genericity there. Is that what you mean? Yeah. And I think that it's true also for, you have a transition from wrinkle to period double. This one is really difficult, and there is no satisfactory mathematical description of it yet. That's the white whale of the subject. So, because it's important to get it in the right setup, what I want is to really consider the simplest problem, which is a thin film where the film is actually growing. And to do that, I'm going to use morphoelasticity, which Derek already presented. And these are ideas, just like Martin explained this morning, coming back from the 90s and so on, which we've played a lot with. And a few years ago, we realized the theory for one-dimensional structure, which is much easier, hadn't actually been done at all. So we played a little bit just trying to formulate it cleanly with Derek Moulton and Thomas Lessing. So the basic idea is that you have a reference configuration on stress. It can grow, so you have a mapping from here to here, which is just the stretch. And then you can, on top of that, you can have elasticity, right? So you want to, essentially you play at all time with 3 different configurations instead of the 2 configurations that you play with regular elasticity. In fluids, you can get away with a single configuration, but here for growing elastic solids, you really need 3 different configurations so that you can really model all the effect that you want. So you have growth stretch and an elastic stretch, and it's just elementary calculus that the total stretch is the product of the 2, right? It's just change of variable between going from here to here. So we have alpha elastic stretch, gamma growth stretch. So we are in 1 dimension, where we have a film in 1 dimension. And so the simplest toy model, it's not yet the simplest, but the basic toy model that you can use for that is to have a rod being on a type of foundation. And the equation for the rod, where F and G are the contact force in the X and Y direction, is essentially given by T's, and theta, as we've seen before, is the angle between the tangent and a fixed direction, in this case the x-axis. So balance of linear momentum, balance of angular momentum give you a nice set of equations. And gamma G here is the effect of the foundation. Okay? To really extract the linear behavior of this equation, since it is a still 4 equation, you can go 1 step further. We usually go directly, but for the explanation, you can really extract what's going on if you do small deflection, right? In fluid, you call that lubrication approximation. So small deflection and vertical motion, so you call W essentially Y of S naught, just that expansion there. And then you get the Euler beam equation out of that, and it has an extra term. There is no Timoshenko beam because we don't have inertia or any dynamics. We only do statics here because we assume that we have small growth and a viscous elastic process in the background that will always take you to the static solution on these time scales. So the important parameter here is the bending stiffness, eta EI, so think of it as a single parameter, the force, the contact force along the x direction, and here is the foundation force. Looks like a very simple equation, and if gamma G is simple enough, it is indeed a very simple equation. So here, the force that is generated, we assume it's growing, so it's pushing against the extremities. We put 2 walls, it's growing against the extremities, so the force, the compressive force is just going to be EA, the area, times the Young's modulus, times gamma minus 1 for the growth process. Right? So now we have an equation, it's almost linear. We have to say something about the foundation. So the simplest case is the Winkler foundation that dates back to 1867, where he was looking at railroad track sleepers and the deformation, is to assume it's linear in the deflection, right? So I rewrite like that, where beta is just the contrast, the stiffness contrast, which is the ratio of the film, the Young's modulus of the film by the Young's modulus of the substrate. So it doesn't, this delta is just a parameter because we have no idea actually what is this parameter in general, but we assume a form like that. Then you do what you're supposed to do. You look at the evolution of modes. You look at a mode like that, and you find the critical value of the growth at which it would appear as a function of the thickness and the contrast ratio. And you have a nice beta to the minus 1/2 scaling, and the critical wave number scales with these powers, right? And on a finite domain, you can easily build solution like that. All is fine. Okay, so that's the classical Winkler foundation. That's the simplest, but it's in many ways too simple. And it was Biot in 1937 who first realized or discussed, pushed the idea. He says, well, if you're on an elastic substrate, you really have to take into account the deformation of the substrate itself. There is energy there. And his idea is very simple, very 4-page paper. He says, now what I'm going to do, I'm going to assume I have a cosine shape, and I'm going to push on my substrate and look at the traction that it generates on the substrate. And it's a linear elastic problem that you can solve with the Airy function. And what you find is that the response of the substrate to that type of deformation, when you do the computation, when you match it, what you find is that the response of the substrate gamma g, if you have a cosine nx, is cosine nx times n. So that's, I'll go back to this term, but you see it is not w. Gamma g is not w because it has the n in there. So it's a quite different form. If you try to rewrite that as in the equation, you can't. It only makes sense in Fourier space. I'll go back to the meaning, the mathematical structure of that foundation. But it's really not obvious. But once you have that, you can look at the expansion of one mode. You go again in stability, and you get different scaling. See, minus 1/3 and so on. Just I put the previous one. You see there are difference in scaling. And they're not that different. I mean, 1/2 is not that different than 2/3 and so on. People always very obsessed by scaling because they really want, you know, it's the one thing they think they can get right in some way. But for very large value of beta, clearly you might see the difference. But for beta of order 1, you won't see the difference. I mean, they're just going to be parameters there, so you won't be able to see the difference between these two scaling. Maybe more interesting is that if you put the excess growth, so when gamma is 1, there is no growth because it's a stretch. So if I just look at the excess growth, you see that the critical wave number is proportional to the square root of delta gamma. It's also true for the Biot foundation, actually. So you wouldn't be able to see the difference between the two. And it has a term t to the minus 1. So that means that larger growth implies higher mode, thinner film implies also higher modes. So let's go back for a minute to a brain problem. We'll go back to that and see how it works in practice. And you see that, indeed, if you increase growth, then you don't see the difference wave number here because you pass the critical value, but you can reproduce typical patterns that you observe just based on this basic principle. Okay, maybe more interesting is when you look at pathological case between a healthy brain and a schizophrenic brain, which has excess growth at the time of funding, and indeed you find a higher wave number. Now you can also change the thickness, that is, you have delta gamma that's larger. You can also change the thickness, and when you have thinner cortex, then you can trigger what's called polymicrogyria, which is an excess of folding. If you have thicker cortex, then it's reminiscent of lysencephaly, which is a smooth brain. It doesn't manage to fold, and that works very well compared to, it fits the general pattern of the observation. I'm not thinking it's the explanation and all that, but what I'm saying is that it's consistent with that picture, at least, of an emerging elastic instability at the time of folding. Now, the problem, of course, is that we know that it's not the whole story, because wrinkling we understand as a linear instability, but the other type of observation, folding that can occur much later, or creasing, we do not quite understand yet. What we know is that by observation, numerical observation, which are by themselves very tricky, as you reduce beta, you reach to a point first where that instability is lost to another one, to a surface instability that was already predicted by Biot, which means that there is a zero wavelength that's being selected, and you don't have any selection of pattern anymore. So you can have a surface instability, but you can also have creasing when you have this type of thing. And creasing, we think, like an exciting new topic, Actually, historically, it goes back to Willis, A.H. Willis, not the famous John Willis here, that observed for the first time this type of creasing pattern in the rubber cylinder. And it's known in the solid mechanics community as the Willis instability. The Willis himself cited a paper in 1932 by somebody named Dewhurst, but I could never find the paper. So this is the type of instability that you can have. It all depends on that parameter beta. So now the next question is, what is beta in practice? If we want to go back to the brain, what is the contrast between the two stiffness, the ratio of the stiffness? That's a good question. So let's go back to experiment. What do we know about brain elasticity? Well, what we know about brain elasticity, you have gray, it's mostly isotropic. You can do plenty of experiment on that. Extension, compression, indentation, shear, blah, blah, blah. And you look, you say, what is the Young's modulus? And you'll find in the literature something between 350 Pascal and 350 kilopascal. Well, that going back in the 70s, they were probably testing fixed brain, right? That collagen is being cross-linked and all that. Now, the consensus really is that the Young's modulus is somewhere between 500 Pascal and 1.5 kilopascal. So I heard talks where they say, oh, we have a material that's 20 kilopascal that's extremely soft, right? So 1 kilopascal in that range is extremely, extremely soft, extremely square soft. And if you want, you can compare indentation experiment where you compare jello, for instance, to brain matter. And you see jello is much, much stiffer than the brain, twice as stiff about. Now you can say what is the difference between white and gray, where you say white and gray is about the same. Well, white seems to be a little bit stiffer there than the gray. But that's indentation experiment. If you do extension experiment, a multi-axial experiment we've done recently, you'll find the opposite, that actually white matter is softer than gray matter. And to have that instability, you essentially need that the thin film is a little stiffer than the substrate. Not always, it will depend. So the best we can say about the stiffness contrast out of all this is between 1/2 and 2. But that's on fixed brain that you harvest after a normal individual. What you really want to know is what happened in vitro, right, in utero. In utero, what happens is that prenatal brains, very nice study by Ellen and a group just being published, they compare brain, prenatal brain and postnatal brain. And what you see is that before birth, there's not quite as much white here. These are cut right after they're being extracted within an hour. And you see this is really white and this is, and that's an indication that the fat hasn't yet been injected. This means there is not much myelin in the system, there is no myelination. And myelination is a process where the myelin comes around and rolls around the neurons through oligodendrocyte and other sections. And that myelination is really directly connected to the stiffness. So it seems that white matter is actually much softer during gestation than it is after, because it creates all this cross-linking due to myelination. So it's very much, it's quite possible that at the time of folding, the white matter is indeed much softer than the gray matter. But essentially, my second remark is we really don't know the material property of the human brain. Okay? So let me go back for a minute to the biofoundation. So the biofoundation was this term. So what is the structure of that? You can look at it as terms of energy, where you have film and substrate. And the film has this typical form where you have a term related to curvature or bending energy, term related to stretching energy. And the substrate, however, is much more complicated because you can rewrite it, but you really have to rewrite it as a H1/2 norm. So it's an homogeneous Sobolev norm. And that tells you right away that if you want to minimize this total energy, you really start to having non-local effect that appears. Okay, so there is nothing obvious about that problem here now, trying to do it. So using this model might not be the right solution. Maybe this model is at the same time too simple and too complicated to study. And maybe, as we're doing now, and people like Martin are doing, we study the full problem in nonlinear elasticity of two layers. Okay, so I just want to mention quickly the role of curvature. So this was on a thick straight substrate. If you do it on a curved substrate, you can go to the same step. And again, if you do the full reduction, you'll realize that you had a certain number of terms that depend just on kappa. And the first term for the bending is increased by an amount 1 plus kappa something that depends on growth. So it increased the effective stiffness, and it reduced the effective force. So the total force, the total effect of curvature is to delay the instability. You increase the stiffness, you reduce the force. So what you expect on a curved surface is that the pattern will first appear at the place where you have the lowest curvature. So if you do it on an ellipsoid, okay. If you do it on an ellipsoid, you'll see the pattern appearing on the flat part, right? And then you can go back to animals which have more or less elongated skull and all that and see how the pattern set up. So I just have a little bit time. I probably never get to the skull, but I want to go to a second story, which we're trying to understand the variation of thickness between gyri and sulci. So it was observed back in early century, 1908 and 1929, that typically the gyri are much thicker than the sulci, right? So the standard explanation for that is that, or the modern explanation is that related to positional information. At the place where there is more growth, if you have a little patch green here, and it grows more than the rest of the film, it will always end up at the top. If the patch is at the bottom, then it will always go back. If the patch doesn't grow as much, it will always go below. So the idea is that less growth turns into sulci and more growth turns into a gyrus, right? But it doesn't imply the opposite. It doesn't imply that a gyri is always connected to more growth. So the simple question, it's a fundamental question about positional information in developmental biology, is do you need information about where to place the gyri and sulci, or by itself, homogeneous growth would create the same pattern? So the first thing that we did is we look at brain, at an MRI of brain, and we plotted the cortical thickness of gyri and sulci. And you see that indeed there is a big difference. Then the reviewer were not happy. He says 9 brain is not enough, you need more brain. So here is 564 brain, and now the p-value is 10 to the minus 200, that there is a difference, which is what this picture is telling you. There is a difference between the two distributions, right? So the sulci are always thinner than the gyri, not always, but certainly as a general principle. Then they say, well, you haven't shown that on fetal brain. We found that it's almost impossible to do it on fetal brain, but we found a nice group of people that have 73 brain and that have looked at a longitudinal study starting in year 0 to adulthood. And they find that indeed there is still growth between years 0 and 1, and it's saturated depending on the different lobes, you see, and that there is always a separation even at birth, right? So we can go back to the point at 30 weeks, but that's the best we can do. And this is a map of thickness of the brain. Overall, we look that the total set is about 100,000 sulci and gyri in 3 dimensions, really, to extract. So that was nice, and that reminded me of a paper by Areski and his student, Eric Sultan, who had done a nice experiment on gel. And then I went back to the paper, and I saw that indeed, even in this experiment, the gyri are always thicker than the sulci. And we redid this experiment, and you see that indeed, if you look at all the ratio, it works very nicely. You always have that difference. So even in a purely physical experiment, this is naturally born. So obviously that's not enough. Then you do simulation, and simulation again shows exactly the same, with a bifurcation right at the point where it emerged at wrinkling that has 2 different shapes, very characteristic in a way. Okay, so that's not enough, so you go to the theory and you do the full minimization variational problem and look at the linear instability and do a weakly linear analysis to understand the evolution of that profile post-bifurcation. And here I use a method by Martin and Pasquale. And I think if you go to Dundee, you'll hear more about that. Don't have time to go through that. But what you get is also that. And you have a difference between the growth of the gyri versus the sulci. They do not scale the same way. You have a linear scaling in the amplitude, which implies a square root scaling in the growth for the sulci, but not for the gyri. So you do have, the bifurcation is not symmetric, just like the experiment and the computation showed. So that's quite a nice overall picture of that we have all these different aspects. And the conclusion is that there is indeed a clear difference in sulci and gyri thickness in both brain and thin film instability. You can go and say whether or not that's one explains the other. What is very nice is that you see this symmetry breaking as a generic feature of wrinkling instability. So I'm going to skip all your questions, and I'm going to go quickly and tell you a little bit, because I'm sure the next question would be, tell us about skull growth. So I'll go quickly. I had to put a quote of Darcy Thompson, like everybody, so you just read it and we go on. He has a nice quote about the fact that both skull and brain have to be an harmonious process of growth. But how do skulls grow? It's very interesting. And the leading explanation is that it's the theory of hand in glove, that the both are really connected, that there is really no space in between, and the two are connected one against the other, and that the brain is driving the growth of the skull by mechanical effect. Okay, and you can see that, for instance, in this picture, this is a normal baby, but if the brain has some kind of very sad disease related to the Zika virus, the brain doesn't grow as much and essentially doesn't push the skull out. Okay? Here is another example of the mechanical effect that you can have on the skull. Okay? At first, the skull it's bone, but it's soft bone, so you can deform it. So it is a tribe in Africa, and this is in Peru. We found this skull. It's good for people who like alien stories, because you can. But actually, in Europe, we still also seem to enjoy this kind of thing. So in Europe, people used to put a scarf around the head of babies in order to protect them either from shock or from heat or from cold and things like that. So for instance, this French person here, you see has a very flat skull here, if you look like that. Okay, here is another case. There is a very nice paper by Broca in the 19th century studying that. It's called the deformation toulousaine because in the south of France it was typical, people typically did that until mid-19th century. Okay.
That's where I'm from.
Yes. Congratulations. They didn't do that to you, your mom? No?
Well, no.
Show me your sides. Can you rotate your head? Okay, more interesting for us, and some irony with the Newton Institute, is that there is a cast of Sophie Germain, the French mathematician, and she had the same deformation because she went through the same process as a baby. The irony, of course, is that she wrote the first treatise on elastic membranes, not really realizing that it actually applies also to a skull. Right? Okay, so the process of the skull growth, I'm just going to go to the mechanical process, not the biological process to which it is that there is pressure at the brain, and at the suture between the brain, between the plates, there is cartilage. And when that cartilage is being pulled, it actually grows. And there is a second process of surface growth where part of the inner surface is eroded and another layer is put, so that the curvature can be remodeled. Because you start with a high curvature and you want to relax this curvature as you go along. Otherwise, you'll have really bumpy patch. The process of growth in the skull is that it can only grow on line, but the whole surface has to grow. So if you want to dilate the shape, you can add material, but you have to change everywhere the curvature. So you have the volumetric growth of the brain, you have the line growth at the edge, and you have surface growth, all this process at the same time. So you can get nice scaling out of that relate the three of them at the same time. You can say, okay, simplest model, I have an arbitrary closed surface. How do I do if I grow it along lines? How do I do so that it remains the same shape? The shape remains invariant. And you really realize that the growth of the brain the growth along the edge and the remodeling of the surface have to be very tightly connected. And then you realize, just like the standard biological explanation so far, is that this can only happen through mechanical process, okay, through mechanical stimuli. And in the pathological case, if you fuse this line, it's quite bad. This case, it's a pathology called craniosynostosis that occurs in babies. If the fusion comes too early, for instance, if you fuse too early the midline, here, the skull would naturally elongate. Again, the brain drives the growth, tries to reach a certain size, so it would elongate the skull. And you can do surgical operation to try to change that. So, or you can try to model it. So here is an ellipsoid with the different patch representing the different bone plates. And depending on the type of plates or the suture, you have different type of growth. The red extend along this line, the yellow along this line for the coronal and lambdoid, and this patch in the middle, which are the fontanelles, the place here, expand both ways. I'm almost done, Eric. So the model, you can calibrate it on the healthy case, and then you turn off, you do suture that turns off certain patches. And when you do that, you recover all the case with the same type of geometry, and you can get one step further and actually measure the cranial index, which is the ratio between the short side over the long side, and get very close by. So it's quite nice in a way because it shows that what the observation about the change in the different, the aspect ratio of the skull is really mostly driven by geometry and mechanics only. Right? And when we started this process, people would tell us, no, you can't, possibly it's way too hard to model. But in a way, here I think you can extract most of it. Okay, and I've taken my time for my questions, so thank you again.
Even though officially he's taking a sample question, I propose we still give him one question. Anybody has one question? Yes, Lisa maybe. Yes, please.
Each time I do the same seminar, somebody asked me the question of the ménage.
Oh.
The role of in this story.
The ventricles, yeah.
The ménage, oui. So I don't know what to answer.
So yeah, it's an interesting question that made me think about something also, because one of the point of the review is as well there is pressure applied during the process, which is the effect of both the ménage and the ventricles in the growth process. How does that affect the instability? And actually, I convinced myself that it shouldn't affect much of the instability because the pressure is basically carried through. But I've not yet done that computation where you look at thin film instability, where you actually have fluid pressure on both sides, where you have a gradient of pressure. I don't think it's going to change, but I think it should be done, yeah, definitely.
Thank you. Let's make Alain once more.